Okay, I'm going to talk mostly about ALiBi. That's why the header says ALiBi, but I'm also going to talk about some stuff we did in Shortformer. And you should ask me a lot of questions. Even though it's my generals, you should ask me a lot because I really like questions. Okay.
Because it's your generals.
Yeah, some people are like stressed. They don't want to stress me out, but I'm not. Okay. So this whole thing starts with the attention is all you need paper. And deep in that paper, they have this quote where they say that transformers may extrapolate the sequence lengths longer than the ones encountered during training. And so the first thing that we did in ALiBi is we actually tested this claim. So this claim was made in 2017, but nobody actually looked into it in a paper. And so the first thing that we're going to do is we're going to figure out if this claim is correct. Can transformers actually do inference on sequences that are longer than what they saw during training? So here's how we're going to test this. So we're going to train a language model, and L is going to be our training length. And here L is going to be 1,000. And we're going to train it on Wikitext 103, which is a data set of 100 million tokens. It's pretty small by today's standards, but it's 100 million tokens from featured articles on Wikipedia. And we're going to train a 250 million parameter model, which is, again, kind of small with today's standards, but later throughout the paper, we'll have bigger models. And so this plot looks really, really silly at first. But this is how we kind of talk about language models in the current literature, like before ALiBi. We train on 1,000 tokens, and then we do inference on 1,000 tokens. And I'm going to show you the developments of perplexity, which is at 17 or 18. So up until ALiBi, that's what everybody did. They would train on 1,000, and then they would do inference on 1,000. And now what we're going to do is we're going to make this interesting. And now we're going to do development set in perplexity on more than 1,024 tokens. So we train on 1,024, but what happens if we feed into our model subsequences of length 1,025? So our expectation as humans is that if you give me more context, I should make predictions that are slightly better if that context is helpful for me, or just as good if that context isn't helpful. That's what I expect to see. So I expect to see, as I input more tokens, I expect to see this line kind of either just stay at the same height if those more tokens aren't helping me, or get better, go lower if those tokens are helpful. And those tokens should be helpful because I feel like Wikipedia articles are really long, and it does matter like what came 1,000 tokens before the current token. But if you take the original transformer, chain sinusoidal embeddings, the perplexity explodes when you give it more inputs, which is crazy. And the reason we're using sinusoidal embeddings is because when they proposed the original transformer model, they proposed two different position embedding types. One is called learn, which is what GPT-3 uses, and I think that's more commonly used. Those types of embeddings have no way to extrapolate, because if you train on 1,024, you have 1,024 positional embeddings. And so if you want to input 1,025 tokens, you can't do that. It's a runtime exception because there's no 1,025th position embedding. And so the other alternative they proposed is a sinusoidal position embeddings, and those are not parametric. And so you, out of the gate, you have as many position embeddings as you want. And their thinking was that those position embeddings are similar enough so that even if you train on 1,024, you should still be able to understand the 1,025th position embedding and 1,026 and so on. But what we show is that it just doesn't work. Empirically, it doesn't work. Performance collapses when you give it more tokens. So we want to solve this problem. We want to draw a line that actually goes down. And so do we want to talk about why extrapolation matters? Okay, let's briefly talk about why extrapolation matters. So,
question.
Oh yeah.
Okay, just out of curiosity, how does the plot look if you go further left when you make it shorter? So it's probably still tracks. Does the complexity still go up or down?
It would go up.
It will go up if you have less complex. So this
Yeah.
is okay.
And
but it won't go up as explicitly, right?
No, not as deep. And we have kind of that later. Oh, yeah. So why does extrapolation matter? So there's a bunch of reasons, but first of all, it could enable our model, which is train short, test long. The length of input sequences has a huge effect on training time. If we could train on shorter sequences, but still be able to comprehend or to process longer sequences at test time, that could save us a lot of compute. We would be able to train on short sequences, but still understand books or long paragraphs or whatever. So it would just save us a lot of time during training. But there's another reason that I mentioned in my slides, which is that we kind of had this ability when we were doing RNNs, right? We would always train RNNs on like short, like 100 or 200 token sequences. But then theoretically, RNNs can handle like an infinite sequence during inference, but transformers obviously don't have this. And so, okay, so we're going back.
Any of the results actually showing up RNNs, were they?
What?
There was no graphs like you just showed that actually worked for RNNs, were they?
No.
Basically, I have exponential moving average. Like they forget everything.
Of course, they forget everything, but they don't explode. So RNNs actually do better than
They don't
this.
get worse. Okay.
Yeah.
Good.
They
don't get
definitely.
better.
You'd probably get diminishing returns in terms, like longer lengths would probably stop.
And they're exponential.
For sure, they definitely they don't understand anything that's like more than a few hundred tokens away, but they don't explode. This explodes. This is like much worse than RNN. Yeah. So what we decided to do to start this exploration is to just change the position embedding that we use. And so the first thing that we try is this thing called the rotary position embeddings, which are like super complicated math, but none of that math matters. What they really do is they, instead of adding position embeddings to word representations, they dot product position embeddings and word representations. So it's just a small modification to the sinusoidal embeddings. And they seem to do just a tiny bit better, but not really. So that didn't really work. Now, the second thing we try is what we call in the paper the T5 bias. So there's this really famous model called T5. And what a lot of people don't know is that when they introduced this model, they also introduced a new type of position embedding, and they didn't even name it. They barely talk about it in the paper, but it's a very unique and new way to model positionality. And when we just took that position embedding method and we put it into our model, it actually really improves performance. And this model, so this model has nothing to do with the T5 model. We just stole the position embedding from T5 and put it into our causal language model. And we train on 1,000, and we're able to actually improve performance all the way up to 2,000 tokens. But then it starts degrading. But we actually managed to kind of make extrapolation work. So our second conclusion is that extrapolation can be enabled by simply swapping the position method. So when I started working on this, we thought that it would take a lot of work to enable extrapolation. We thought it would require changing the attention mechanism, changing the position embedding method, just a lot of things. But it seems like just changing the position embedding method has lots of power and can really impact performance. And this is ALiBi. It's awesome. Okay, any questions before we talk about how ALiBi works?
Can you define awesome? No, kidding.
Okay, so ALiBi is super simple to implement. It's in one easy step. Step 0, comment out the positional embeddings. So you go into your code and you comment out positional embeddings because there's no positional embeddings in this method. And then step 1, we're going to add a bias to the attention scores. So we're doing causal language modeling. We're trying to predict the next word in a sentence. And so to do that, we use the last word as the query and all the previous words as the keys. And we perform these dot products, right, to compute attention values. And usually we just perform dot products and then we normalize them using a softmax, and those are our attention coefficients. We're now going to just very, very gently modify the way we compute these coefficients. We're going to negatively bias these values in a way that increases as the key and the query are further away, right? If we're reading a sentence and these two words are really close, they probably really need to interact with one another. They're probably really important to one another. But the further we go, like these words probably don't really matter much to one another. And that's what this bias encodes.
Those numbers there are vectors.
Oh no, these, so your dot product.
No, part this first.
What?
Dot part this first and then the number.
Yeah. So you dot product, you get a number, and then you subtract this number. So everything's a number. Other questions? So if you do this, it won't actually work very well because these numbers will get big too quickly. So we normalize these numbers with just a different number m, which is a float between 0 and 1. And then the really cool thing we can do, this is a critical part of ALiBi, we're actually doing multi-head attention, right? So today nobody really does single head attention. So whenever you attend, you're actually doing attention with 8 or 16 or 32 different heads. So you're actually attending to this sequence 32 different times. And because we have this normalizing float m, we can do something really cool here. We can use, if we have 16 heads, we can use 16 different m's. And what that does is now we have this distance bias, which grows in different ways. So if m is really close to 1, if it's really big, that means that this function is going to increase really, really quickly. And so this bias is going to become big very, very quickly. And so those heads are going to look at very, very, very few tokens. They're going to look, and I've seen this empirically. I can look at what the model is looking at. And I can see that heads that have high m values, they only look at like 5 or 6 or 10 tokens away. Their attention is very, very constrained. Some m's are going to be very, very low, very close to 0. And so for them, this function will increase very, very slowly. And those heads will look at very, very long context ranges. So like 1,000 or 2,000 tokens away. And so when implementing ALiBi, I've found it to be critical to have different m values and kind of have this inductive bias that forces heads to behave differently, which is very different than the normal transformer model, where every head is kind of initialized. They're initialized differently, but their actual functionality is the same. Like there's nothing that constrains them to act differently. Here we have this very hard constraint that makes each head act differently. Oh, and what I didn't mention is that m is not trained. M is manually set. I'll talk about why in a second. But we have this geometric, it's a geometric sequence. It's a very simple geometric sequence. And we just have this function. If you have n heads, this is your starting number, and it's also the ratio for the geometric sequence. So you just have these geometric sequence of m values. And I found that to work really, really well across many different NLP tasks. I've also used this for like image and transformer. These m values just seem to work really, really well. It's just a bunch of values between 0 and 1, such that their density grows as you get closer to 0. I found it to work really well. Training m, some people do that now with ALiBi, but it runs a tiny bit slower, and sometimes you run into some issues. So I just prefer having the manual values because they just work really well and it's really fast, and yeah, it works. Okay, questions about how ALiBi is implemented? Yes.
Do you think it would break if one of the heads actually had m equals 0?
Oh, yeah, that's a good question. If m equals 0 for just one of the heads, it's totally fine. It doesn't improve performance, but it also doesn't hurt performance. And then I would play around with like, studying 2 heads, that's still okay. But then like 3 or 4 heads equal to 0, it starts degrading performance. And the same thing is true for if you have like multiple m values that are set to be the same. If just 2 of them are the same, it's fine. But if you were to set all of them to be the same, it would really hurt performance. Yeah. So you should have like different values, and yeah, setting one of them to 0, it doesn't hurt, but it also doesn't help. So I don't really do that. But that would mean that you kind of have a positionless. A head that kind of isn't really aware of positioning.
Right.
But that's also not true because we have a different paper that shows that even when you don't have any positional biases or any positional vectors, transformers can still deduce where they are in the sequence by just looking at the number of tokens that they are attending to. Never mind, that's a whole different thing. Any other questions about the ALiBi implementation? Yeah.
Could the bias have been non-linear, like square root?
Oh, yeah. When we were writing this, Mike was really pushing for like some kind of square thing, all kinds of crazy stuff. But I've not found anything that's nonlinear. I've tried a lot of nonlinear things. Okay, not a lot, maybe like 5 or 6, but I haven't found anything that beats linear. Linear is so cool, it's so simple and so easy.
If you use this with like other existing position and other like T5 bias, does that improve performance further?
The T5 bias, I'll talk about it in a bit. The T5 bias is too similar to this for it to make sense to use them both at the same time, I think. You could try, I don't think it would help, but you could do like sinusoidal and ALiBi, you could do that. It's a really bad idea. It's not, maybe I'll talk about it later, but it's just, I think that we should not use positional embeddings because they lead the transformer to overfit on the position embeddings. I'll talk about that in a bit. Any other questions?
This is just a very far-fetched thing. I was also going to ask the non-linear question, and
Oh yeah.
I was thinking, and I highly doubt this would actually help, but one thing that could be cool to try is there's lots of cross-linguistic data about dependency length in
Yeah.
all kinds of languages. And so you can imagine the bias actually coming from what we know about dependency length in the languages of the world, and just using that distribution as the bias.
Yeah.
I doubt it'll actually improve over just the linear one, but it's something more principled than just trying different functions for the
Yeah.
bias.
You're saying like you use a lower M for Spanish, for example, than English?
No, I mean, like, instead of just going linear, there's like the distribution of the length of dependency arcs is known cross linguistically. So you could just look at sort of how often do you have like one dependencies, how often do you have like two
And it's much
dependencies?
sharper. It's much sharper, right? Like
Yeah.
the vast majority of syntax is local.
Yeah,
The
exactly.
vast majority of attachments are like 1 or 2.
Yeah,
and
yeah.
it falls off.
Yeah, there's like pressure to minimize it in general.
Yeah. I guess maybe like, specific small differences maybe don't matter that much. What matters is that a lot of these heads are very, very local, like 5 or 6 or 10 words. And then there's just 1 or 2 heads that look at it. I think there might be I think the smallest head only, in one of the models I trained, I saw that it only looks at like 1 or 2 words back. So I'm going to briefly mention how we implemented this. It's basically just a matrix addition, right? So you have your key times query matrix. And these are the attention values, right? The dot products of the keys and the queries. And then we do this thing where we compute all the dot products, but we mask out the top right triangle because we don't want you to attend it to the future. And to implement ALiBi, you just add, you make this matrix in PyTorch or whatever. And then you multiply it by M and you add it to your attention matrix. So this is like the naive implementation. And when I initially implemented this, it was running like 5% slower than the normal language model because apparently really small changes to the architecture can make really big, can lead to really big time increases. And so there's a small trick that we use in the actual implementation of ALiBi where we make it run just as fast as sinusoidal by adding this matrix to the mask matrix. So this isn't a great way to visualize this, but instead of having 3 matrix additions, which is what we had in the initial implementation, so you would always have your attention matrix, and then you would add the masking matrix, which would mask out these.
The mask
values.
is an addition, not a product.
It's an addition.
Yeah, actually, that's weird.
That's super weird.
You add negative infinity.
Nice.
Yeah, I don't know why that's what we've been doing. So usually you'd have, in the native implementation, you'd have 2 matrix additions, right? You'd have the attention matrix plus mask plus ALiBi. But what I did was I just set mask at the beginning of training, just one time. I set mask equals mask plus ALiBi. And then now it's just one matrix addition. It's just attention coefficients plus ALiBi, plus mask / ALiBi thingy. And that makes it just as fast as the sinusoidal method. So there's no runtime penalty for this method. So that's it. Now I have a bit of a sales pitch here. We don't have positional embeddings. It runs just as fast as sinusoidal. Does not require additional parameters. T5 does. And sometimes it requires a bit of extra memory to make this whole thing work. But yeah, it's really efficient. More questions before we talk about the results?
So if you're using like sinusoidal embeddings, for instance, and in your matrix, you mask everything that's more than 1024 long, that would give you like a flat line on your initial plot. Right, like you're basically preventing the model from seeing anything that's past 1024, so you have the same complexity.
Okay, so let's talk about, we can talk about this now, it's a good question. Let's talk about why this happens, why the numbers here explode. I have more slides about this later, but I believe that transformer language models trained with position embeddings overfit to specific position embeddings. So a transformer doesn't have, I hypothesize that a transformer thinks that dog at 5 and dog at 6 are two different but similar concepts, which are similar but different to dog at 7, which is similar but different to dog at 8. It doesn't really, when we gave it position embeddings, we didn't want it to kind of remember anything about dog at 9 because there's nothing special about dog at position 9. We just wanted to understand the relative distances between words, but what it ended up doing is it ends up overfitting to specific positions. And the only reason that GPT-3 or any of these models work is because their training data sets are so massive. They've just seen every word at basically every single position. And that's why we kind of feel like they can kind of generalize the stuff, but they don't. If you give them position embeddings, I really believe that they overfit to specific position embeddings. And I have a bunch of experiments that really make me strongly believe this claim. But I think that what's happening here is that we train it on 1024, and then you give it 1025 tokens. So now it's seeing dog at position 1025 or whatever word at position 1025. And it explodes because it's like, you know, dog at position 1025. What is 1025? I've never seen this before. And I go, one of the pieces of evidence I have about this, which we might talk about later, is that this model, you can't see it here, but when you train a 250 million parameter model, it actually can extrapolate to 50 tokens more than what it was trained on. So if you train 1024 and you give it 1025 or 1026, it can actually do okay, and it only starts exploding at 1070 tokens. On the other hand, when we trained a 1.3 billion parameter model, it exploded right away. So we gave it, we trained on 1024, we gave it 1025 tokens, and right away perplexity went through the roof. And we know that larger models have more capacity, they overfit more. And that's one of the pieces of evidence that makes me think that transformers overfit to specific position things. And so what Gabe was proposing, he was proposing that we solve this issue by building a transformer that trains on 1024, and we can constrain the attention matrices to only look at 1024 tokens back, right? So we train on 1024 and then we feed it 1025, but we're telling it, hey, this is timestamp 1025. You have 1025 tokens that you could look at, but we're going to constrain to just the last 1024. And we could do that all the way up to 16,000 or whatever. And so Gabe was like, oh, that would have solved this issue. You would have gone a flat line, but that's incorrect. You can try this, and because of this overfitting to specific position embeddings, the second that you give it a position embedding that it hasn't seen during training, it'll just explode. So it's not exploding because it's seeing more tokens than it saw during training. I mean, I'm sure that that's part of what's happening, but it's also exploding because it's seeing position embeddings that it didn't see during training, and that's really confusing it. And so even if you did take the original transformer and you constrained it to just look at 1024, it still would not be able to extrapolate and maintain that flat line, which is what RNNs could do. RNNs could maintain a flat line even when taking more tokens. They wouldn't improve, but they also wouldn't degrade. Transformers degrade because they overfit specific position embeddings. So even if you constrain to look at the last 1,000 tokens, they're still going to explode because it's just going to confuse them. Other questions? I think now, yes. Now it's results time. So whenever I find something that works in language modeling, I'm always really paranoid that maybe I programmed something incorrectly and it actually doesn't work, and I'm just, I just have a bug. And so I only can really relax when somebody else has re-implemented my thing and tells me that it works for them too. And it's even more relaxing if it's like big science or whatever, and they have like 20 engineers implementing it. But big science implemented ALiBi, they implement like a lot of things to check what works for large language models, and they trained a bunch of 1.3 billion parameter models. And they not only use perplexity to evaluate these models, but they also have a suite of downstream tasks, which are a lot of the same tasks that GPT-3 was tested on. And so they just tried a few different position embedding methods. And EAI is their suite of downstream tasks. And ALiBi does what?
Higher is better.
Yeah. I think it's like out of 100. ALiBi does much better than everything else. So you don't even have to trust me. It works. And now we're just very briefly going to talk about the results from my paper. So ALiBi works really well, but because it's a really cool. Oh yeah, for sure.
So I thought the original argument was more about generalizing the longer sequences
Exactly, yeah.
rather than improving on
So-
both. So what's going on there?
Oh yeah, it's a good question. So ALiBi is like one of the first position embeddings that allows you to extrapolate to longer sequences. But not only does it allow you to extrapolate to longer sequences, even if you don't care about extrapolation, because none of this is extrapolation. They train models on, I think, 2,000 token long sequences, and then they test them on 2,000 token long sequences. But even if you don't care about extrapolation, it seems like ALiBi is better. ALiBi is a better way to look at your input. It seems like this constraint, this distance bias is just a better way to look at your input, even if you don't care about extrapolating to longer sequences.
So are they using it in the big model?
Yeah. Bloom uses ALiBi. Other questions? Okay. So the results are cool at the 1 billion parameter scale, but they're even cooler when you have like the limited resources, because then that inductive bias is even stronger. I think that when you train a really big model, you have so much capacity, you have so much training time. I think the model, through time, it understands that it should really, pay more attention locally and pay less attention as you go further away. But when you have very limited training time and very limited data, it's much more powerful to give the model this information kind of automatically through this inductive bias that we use. And so for small models, what you're going to see is that the results are really crazy. So what I did here was I trained, I think it's 5 different sinusoidal models on Wikitext 103. So these are 5 different models, each trained on different input links. And now I'm going to train one ALiBi model on 500 tokens. So as I said before, we do better even when you don't care about extrapolation, right? So we do slightly better than the sinusoidal model. But the crazy thing is that now with ALiBi, we can stretch our model and read sequences of size 1,000 and 2,000 or whatever. And we can stretch our model and it does better. So for example, we can stretch our model trained on 500 tokens to 3,000, and it does better than the sinusoidal model that was trained on 3,000. So that's really, really crazy. Yeah. Because the 500 model took like a fourth of the time. I don't know. It took much less time to train. Questions? Okay. And then if you train on longer sequences, it does better. But yeah, Wikitext 103 used to be the kind of benchmark that we all used for developing language models like 5 years ago. And I remember when it first came out, we were like, oh, this is so big because it's 100 million words. Pentry Big was like 1 million words. But now Wikitext 103 has become a toy. Nobody can really trust results from that. So now what we're going to do is we're going to go into the real world with a suit. We're going to train on this internal Facebook dataset that was kind of built to kind of replicate the dataset that GPT-3 was trained on. So it's 461 gigabytes. It's all these datasets. And our baseline has 1.3 billion parameters. It's 25 layers using the sinusoidal embedding. And then we're going to train our model. Sorry, and the baseline is trained on 2,000 tokens, just like GPT-3. Then we're going to train our model. And the only difference, there are going to be two differences. And the first one is that we're going to use ALiBi, and the second one is that we're going to train on sequences of size 1,000, right? So we train faster, right? Every one of our iterations is faster, and we use less memory. So this is kind of an unfair comparison. I'm giving my model much less resources than the baseline model, but we still beat the baseline model. So our model is the blue line, the baseline is the yellow line, and we're using much less memory. The x-axis is just training time, but we still manage to slightly beat it. We're comparing both models on sequences of size 2,000. So ALiBi seems to always do better than sinusoidal. The gaps in this limited data setting are huge, just crazy good. When you go to larger models, ALiBi is still better, but by a more realistic gap. And this is extrapolation. So I kind of teased this 5 minutes ago, but if you try to extrapolate with the sinusoidal model, so the yellow dot here, you can barely see it, is how much complexity it gets for 1,024, and then you give it 1,025 tokens, and it immediately starts doing worse. Whereas the smaller model, it could handle like up to 50 more tokens, but the larger model really overfits the position embeddings. That's my belief. And it really explodes quickly. Whereas our model in this setting is able to extrapolate to 2 times its training length, and then it starts degrading. I'm not quite sure why, but yeah. Talked about this. Analysis. Okay, any questions about everything we've seen up to now before I talk about analysis? So I think that ALiBi is really cool. And it's a very big step forward. But it doesn't do everything that we think it should do or could do. And in this section, I'm going to explain it. So we've seen that with ALiBi, it gets better perplexity as you input longer sequences. And the question that I want to ask now is, are we getting better perplexity because we're actually using long range patterns? Is ALiBi actually able to consume 1,024 tokens during training and then actually effectively look at 1,025 and do better? Or is there something else going on here? Yeah, why does perplexity improve when it increases? And in order to understand what's going on here, I'm going to talk about the early token curse, which is a concept that we talked about in Shortformer, which is a previous paper. So this was pre-ALiBi. What I did was kind of like I did in ALiBi, I trained 8 different models on 8 different sequence lengths. And what I saw was that, and this is pre-ALiBi, right? So you train a model on L and then you do inference on L. And what you see is that as sequence length grows, perplexity goes down. And so for a long time, people thought that training on a longer sequence, the longer you train on, the better. Well, what I'm going to show is that that's actually not the case, and that this conclusion that training and longer is better is a conclusion that can only be reached if you use a faulty evaluation method, which is the evaluation method that most people use to evaluate language models. So non-overlapping evaluation is what we usually use to evaluate language models. So what we do is we have this really long test set or development set. It's like hundreds of thousands of tokens, or millions of tokens. And we'd like to compute perplexity for it. And what we'd like to do is we'd like to feed in this entire dev set into the model and get the perplexity. But we can't do that because it's like, 100 million tokens or 10 million tokens. No computer has enough memory to handle that. And so what we do is we segment this dev set into non-overlapping segments, and then we evaluate them each independently, and then we combine all those perplexities. And there's a huge issue with that, which we call the early token curse, and that's what we talked about in this previous paper. And I'll explain to you what the issue is. So let's say we have two different models. One of them is trained on sequences of size 512, and the other is trained on sequences of size 1,000. If I train a language model, so what I previously showed you was that Alyssa is laughing, probably because she noticed that my segments aren't equal. I don't know how to do the Photoshops inside the Google Slides.
It shows.
I'm not getting an art degree. Anyways, so what I showed you before is that if I train a language model on 512 and Alyssa trains a language model on 1,000 tokens, Alyssa's language model is going to have lower complexity. You might think that Alyssa's model is better at modeling language, but that's not correct. What we're going to show here is that Alyssa's model is getting a better complexity because the task that it has to complete is a much easier task. And here's why. When you do language modeling, the toughest tokens to predict are like the first 5 tokens. Those are the tokens in which you have the most ambiguity. You have no idea what the hell you're supposed to talk about. So there's a lot of ambiguity, and the loss there is huge because your predictions are really wrong. And so this early token environment is where most of the loss occurs. And Alyssa has half as many early token segments that she has to deal with compared to me, right? So I'm gonna highlight all the early token areas. This is more of the art degree. And Alyssa, because her model runs in sequences that are twice the size as my model, she has to deal with much less early token segments. And that's why her perplexity seems better than mine. That her task is much easier than mine. And so it's much easier for her to get good perplexity compared to me. I'm going to prove this to you by basically solving away the early token curse by using a different kind of evaluation method, which is called sliding window evaluation. So sliding window evaluation was not invented by us. I think that Bevsky and Ali were the first to do this for transformers, but nobody in the community really used it, and people still don't really use it to compare different models. But here's how sliding evaluation works. Sliding window evaluation works. So let's say I have this 8-word sentence, non-overlapping evaluation would first, and we have a toy language model that can only have 4 words at once. Non-overlapping evaluation would first evaluate the first 4 words and then evaluate the next 4 words. When we do sliding window evaluation, it's going to be on top here. Our first inference pass has to be these first 4 words. They're just going to be an edge case. But for every subsequent inference pass, we're only going to move our model 1 word to the right. And we're only going to ask for the probability of this word. So we're always going to move our model 1 word to the right. We're going to try to predict the last word using all the previous words as context. And this basically totally cancels the early token curse. Because now, at almost every single inference pass, we're only asking for the probability of the last word using L-1 tokens of context. And so we have these 8 models that I previously trained. And the first, non-overlapping evaluation made it seem like, performance got better as sequence length increased. But now we're not going to do any extra training here. We're going to reevaluate these 8 models using sliding window evaluation. So it's really, really, really slow, right? This runs so much slower than non-overlapping evaluation, but it's much more accurate. And now, what we see is that it does help to train longer sequences, but it stops helping at around 1,000 tokens. So we get to extra complexity, and then we stay there. This is like within the standard deviation. This number here shouldn't be highlighted. Like all 3 of these should be highlighted because they're all within standard deviation. And so yes, if you're training on natural language, you can train on 32 tokens and expect to do really well when looking at 1,000. But after 1,000, training on longer sequences doesn't seem to help. Now, I don't think that this is an unsolvable problem. I think that we need to get better data that has more long-term dependencies. We need to build better models. I don't think attention is ever going to be able to handle more than 1,000 tokens. Attention is like a weighted bag of words. You can't really look at 1,000 or more than 1,000 words effectively if you have this bag of words style mechanism. So I think, the data has to be better. Attention has to be better. Our loss probably really incentivizes looking at short-term dependencies much more than looking at long-term dependencies, because long-term dependencies are so rare. So whatever is going on right now, or all of these 3 things, lead to this effect where training on more than 1,000 tokens does not make sense. And this paper was written 2 years ago on small 250 million parameter models trained on Wikitext, but a few months ago at Facebook, I trained a few big models and reran the same experiment, and I trained them on like this massive 500 gigabyte corpus, like massive 1 billion parameter models, and I still got the same result. So this is still true today. But I guess the reason I brought this up is because I just wanted to introduce sliding window evaluation and highlight the importance of it. But now that we have this really cool tool, we can go back to ALiBi. And now we're going to reevaluate the ALiBi models with sliding window evaluation. So up until now, all the models in the ALiBi paper were evaluated with non-overlapping evaluation. And so we saw ALiBi increase in performance as we gave it more tokens. But now we're going to check whether that increase was because of the early token curse or whether it was because ALiBi was actually understanding longer sequences. So I need the legend here, but this first model is the sinusoidal model evaluated with sliding window evaluation. So we train it on 500 tokens, and we evaluate it on 500 tokens, and we get this perplexity. And now we're going to stretch it out to 1,000 and reevaluate it using sliding window evaluation. And perplexity really explodes. Like this evaluation method is better than the previous one we were using, and it really shows that sinusoidal language models cannot extrapolate at all. Like it explodes so much that this line looks vertical. It's not vertical, but it's almost vertical. Now we're going to do the same thing for ALiBi. And now we get a different result than what we were getting before. Before, it kind of seemed like ALiBi was getting better as we get the longer sequences. But now we train this model. So again, this line represents just one model. We train it on 500 tokens. Then we're stretching it out to 1,000 or 1,500 or 3,000 tokens. And we basically get a flat line. And so this tells us that ALiBi is able to, you can train on 500 and stretch it to 1,000. And it's able to consume more tokens, but it's not actually using that extra context that it has. ALiBi basically, if you train it on 500 tokens, it'll be able to consume 1,000 tokens during inference, but it's not actually going to, at every time step, it's only going to look 500 tokens backwards. So now we've kind of managed to implement the sliding window idea that Gabe had that doesn't really work with sinusoidal models. ALiBi is basically so forget sliding window evaluation for a second. ALiBi is basically a sliding window kind of model like RNNs where you can train on 500 and then at inference time, you can give it 1,000 tokens and it'll be able to consume these 1,000. So if you give a sinusoidal model 1,000 tokens, it just explodes because it hasn't seen those last 500 position embeddings. If you give our model 1,000 tokens, it works, but at every time step, it's only looking 500 tokens backwards. So we've managed to make a really big step. We can now have models that can consume more tokens than they were trained on. But at every time step, they're local. They only look at as many tokens as they were trained on. So there's a very big step here, but there's also a lot to be done. How can we build models that can be trained on 1,000 tokens and then actually effectively use more than 1,000 tokens during inference?
One quick question. You had this very nice experiment earlier where you compared train at 500, extrapolate to 1K to train at 1K. But that was before you introduced the sliding window.
Yeah.
Do you have a version of the plot with the sliding window evaluation?
Yeah. So what I do is I put white boxes. So here it is. So yeah, so if you train on more, it's better.
I see.
But there's always this straight line.
Earlier we had the effect that 512 training plus ALiBi extrapolation match training at 1024.
Exactly.
Now it does not match.
Yeah, it doesn't happen. So training ALiBi on longer sequences is better, and extrapolation just remains flat. It doesn't actually improve performance because it's only looking at 1,000 tokens or 500 tokens back. Okay. Okay, that's it for ALiBi.